application in chemical engineering for the first order differential equation. The problem statement saying that we have the reaction A is the reactant and B is the product. This reaction occurs in the batch reactor. This reaction is first order reaction. It is found that 65% of reactant A decomposes to the product within 30 seconds. Find the fraction of reactant A remaining in the reactor at 4 after 1 minute. After 1 minute, okay? So, I'm not sure like all of you have learned about batch reactor before, or in the batch reactor we have the design equation for batch reactor, which is saying that dCA by dt is equal to RA. RA is the reaction rate, and we know that A is a reactant, so by the time passing, A reacts to become B. So it's saying that this reaction is first order reaction. That means minus RA, which is this minus saying that A is just, the amount of A is just getting lower and lower. So that means it is decomposed. It's equal to KCA. This is the first order. K is the rate constant. It's just a constant number. But in this problem statement, they didn't tell us that what is the K. Okay. So it just plus, this is equation 1 and this is equation 2. Just plus 2 into 1. I would get dCA by dt is equal to minus KCA. The problem statement asking us to find Ca by the time at 1 minute. After the reaction occurs for 1 minute, what would be the amount of A which is remain in the reactor? So that means we got to know this Ca. Now we have first order differential equation, right? So in order to find Ca, you've got to solve for the answer of this differential equation. And it is inseparable equation. This T is time, okay? It means time. So to do this, this one is separable equation. K is a constant, okay? So the way to solve for it, you just move this Ca to the left hand side of your equation. And then we put T with K, right? And then we do integral of that. K is a constant, so I take K out from the integral sign. Now when we do integral, we are going to put the concentration at the beginning. We assume that when we put Ca, we put it as a Ca0. It's the initial condition of it. It's the initial concentration of A. Okay? At times is equal to 0. We have Ca is equal to Ca0. By the time passed, at T equal to T, we saying that, okay, we have Ca is equal to Ca. That is what we want to know. What would be the amount of A which is still inside the reactor? Okay. So when we do integral dCA by Ca is equal to ln Ca, right? And then we put boundary there. I didn't put the absolute sign there because I know that the concentration never have a negative value, right? The concentration of the substances never have a negative value, which is equal to minus K times T. And then if you plug boundary in, I would get ln Ca by Ca0 is equal to minus Kt, or Ca divided by Ca0 is equal to exponential of minus Kt. Or you can do this way, like you can do like a plus C. I mean, if you don't want to get Ca0, you can do like a plus C, but when you put a boundary condition in, you would get what would be that C value. But usually in chemical engineering point of view, because we know that at the beginning how much we put the substance in there, so that's why we don't like integral and then plus C. We just put boundary condition in there. Now, the question asking us like, what is the fraction of reactant A? When we're talking about the fraction of reactant A, it means that what would be the amount of A comparing with when you put it at the beginning? How what would be the amount of A which is still left inside the reactor when the time at 1 minute? So that means the problem statement asking for this number. But the thing is that you can find it if you know the K value, because for T, which is the time, the problem statement already told you that they want to know at 1 minute. What would be this fraction? You know T, but you can't find this value yet because you don't know K. But part of the problem statement, there's a part of the problem statement leading us to find K, which is the one that I do underline there. It said that when you have the fraction of A about 65%, no, it said that 65% of A decomposed, so that means how many of A still left in the system? 65% decomposed. You put A like 100% at the beginning, but when it's 30 minutes past, you find out that 65% of A decomposed. So what would be the amount of A which is still left inside the reactor? What is the amount of A which is still left inside the reactor when the time is 30 seconds? If we put A at T equal to 0, if we put A 100% into the reactor, and then at 30 seconds, we find out that 65% of A decomposed to be B. So the question is that, what is the amount of A which is still left in the reactor? No, because that 65% decomposed. Yep, so that means 35% of A still remain in the reactor. So that means they tell you that 0.35 is still in the reactor at 30 seconds. Now, Can you find the value of k? Now can you find the value of k? So k is equal to point what? 0, 3, 5. And the unit is per second. Or you can plug into this one. Ln of 0.35 equal to minus k times 30 seconds. So k is equal to minus 1 over 30 seconds times ln of 0.35. And then the value of k is that. Now if you find the value of k, can you find the fraction of a when time is equal to 1 minute? Now you know k already, right? You know k. So the fraction of a remaining in the reactor after 1 minute is equal to 1 minute is equal to what second? 60 seconds. Don't forget to change the unit because the unit of this k is per sec, not per minute. Okay. So what would be the fraction of Ca over Ca0? What do you get? That no, you got to do the exponential of that value. It shouldn't be negative value. The fraction which is left is not, sorry, the fraction of Ca over Ca0 shouldn't be negative. Okay, minus 0.035 times 60 is equal to minus 2.10. That's right. Sure? Don't think so. 0.12. 2 or 3? 2, 2. That would be the fraction.